Hello everyone, welcome to your first unit on inductive and deductive reasoning. In this unit we're going to set the stage for all of the other topics we'll cover by talking about mathematical reasoning and the process of doing mathematics. And we want to answer the question in math, how do we know what we know? So here are some key vocabulary terms, and we'll talk about all of these. Inductive, deductive reasoning, conjectures, counterexamples, premises, and conclusions. And some of the specific things that you should be able to do by the time you finish learning about this topic: explain the difference between these two types of reasoning, identify premises and conclusions, decide if reasoning is inductive or deductive, use the two of those types of reasonings together, and also disprove conjectures by giving counterexamples. So if you're not familiar with those things, then stay tuned and you'll learn how to do all of these. Alright, so your first definition. Inductive reasoning is the process of reasoning that arrives at a general conclusion based on the observation of specific examples. So it may or may not be true, and we often call the conclusion a conjecture because it's more of an educated guess. We're not sure that it actually is a true conclusion. So here's an example. Use inductive reasoning to find a pattern and make a reasonable conjecture for the next three numbers by using that pattern. All right, so here's what you're doing. You're looking at these numbers, and these are our specific pieces of information, specific examples, and you're using those to take your best guess about the three numbers that would come next. All right, so if you want to pause or if you've already decided on an answer, all right, see what you think would be next. All right, and if you guessed, let's see, 8, 6, 9, then that would be a good guess. All right, so some patterns that you may have seen. Notice that every other number, starting with the first one, right, we're just counting up by ones, 1, 2, 3, 4, 5. So that would lead you to maybe think that this number is a 6. And then if you look at the other numbers, 4, 5, 6, 7, 8, and 9. You may have also seen a pattern like an addition, subtraction type pattern. All right, from 1 to 4, you've added 3. 4 to 2 is minus 2. Next number is 5, that's plus 3. Next number is 3, and that's minus 2. All right, so you could use that pattern as well. All right, how about this one? What are the next 4 digits of the decimal number shown below? Use inductive reasoning to find a pattern and make a reasonable conjecture. So again, this is inductive reasoning because we're looking at some specific examples and taking our best guess about what would come next. And that best guess is this conjecture. All right, so what do you think would come next? All right, many people guess 5, 5. And sure, maybe it's that. But what if the actual number has this repeating pattern of 1, 1, 2, 2, 3, 3, 4, 4, and then it starts over again, 1, 1, 2, 2, 3, 3, 4, 4. Tricky, right? All right, so if you guessed 5, 5, 6, 6 for the next 4 numbers, and if the number was actually this number instead, then your conjecture, your guess, was reasonable, but in this case it would have been false. So this illustrates why when we're doing math, we can't know for sure that our answer is correct just by looking at examples. All right, so if you think you see a pattern and you think it continues, sure, maybe it does. And depending on the type of numbers we're working with, that may or may not be likely. But it's not enough just to look at those examples. All right, and some people think if we look at enough examples, then we'll know for sure that the pattern is true. All right, so let's say that with that decimal number, 2, 2, 3, 3, 4, 4. All right, let's say then that you stick with that new pattern. All right, and let's say you use a computer to check the next million digits, and the next million digits all agree with this pattern that we think we've seen. All right, well, that's not enough because the million and 1th number could be different than that pattern. Let's say that every day for a year you see your neighbor walking his dog along the same route. he does this every single day for an entire year, or maybe even for 5 years, is it reasonable to assume that he would always do so in the future? Sure. All right, that's reasonable. But does it prove that he will? No, it doesn't. So on your own, maybe think of a reason why he might not walk his dog on a certain day in the future. Just convince yourself that this isn't, a proven fact for sure. So here's our definition of deductive reasoning. And because we have this inductive reasoning that's helpful in making guesses, but it doesn't necessarily give us true facts all the time, then we have another type of reasoning that we do use to arrive at true statements. And this is deductive reasoning. It's the process of reasoning that arrives at a conclusion based on previously accepted general statements. It does not rely on specific examples. This type of reasoning does prove the conjecture, and it does give a true conclusion. All right, so if we start out with the previously accepted general statement that the Earth is not flat, okay, we accept that as fact now. All right, then anybody who comes along and points to something and says, okay, well, here's an example of why I think the Earth is flat. Right, well, then we can just point to this fact and say, well, no, we know that it's not flat, so we can reason to a number of other things from there. All right, here's an example. Passengers must have a passport to board an international flight. You're traveling from America to France and you forget your passport at home. Right, and we can make a conclusion from this. Right, so this first line, passengers must have a passport to board an international flight, that's our generally accepted statement. Right, we're going to take that as a true fact. Right, so assuming that that is true, then we can reach a conclusion here. If you're going from America to France and you forget your passport, then you'd have to conclude that you're not boarding that flight because that is an international flight. How about this one? All cows have 3 legs. All right, we're going to take this as our previously accepted general statement. Driving by a farm, you observe the animal below. Clearly, this animal has 4 legs. So what would you be forced to conclude? Well, if you're reasoning logically here, right, then you know all cows have 3 legs. That's truth. And then this animal has 4 legs, not 3. So logically, you'd be forced to conclude that this animal is not a cow. And this is a silly example, but it shows that we've kind of locked ourselves into some reasoning here that if you're using deductive reasoning, then you are naturally led to certain conclusions based on the facts that you started with. All right, so we said before that deductive reasoning did prove conjectures, and that is true as long as we start with true principles. All right, so when we speak of a principle, a lot of times we'll just assume that it is true. Right? The 3-legged cow argument, that's valid, but not true. So when something follows the rules of logic, but still leads to a false conclusion because it started with a false premise, then we say that it's valid, but not true. A classic example of this would be the 2 different arguments that begin with 2 different statements. Either God created the earth in 7 days usually, right, or 6 days, rested on the 7th, or the evolutionary theory starting with the Big Bang and evolution as the origins of the universe. All right, so 2 wildly different premises, and if you accept one of these to be true, then naturally you're led to some other, a whole host of facts based on those starting premises. All right, so it doesn't necessarily mean that that beginning statement is true or the conclusions are true. It just means that everything's valid, meaning it's consistent with each other. All right, so somebody could believe in the Big Bang Theory or evolution and be led to some false conclusions, right? Since that is, if if that is false, the Big Bang, all right, but it would still be a valid or consistent system because all of those facts agree with each other. All right, inductive reasoning. Let's look at a few more examples. Make a reasonable conjecture for the next figure in the sequence. All right, so we see, look for some patterns here. All right, pause if you want to. All right, so we see some alternating large circles and large squares. So it seems like the next one would be a large square. All right, then inside we have alternating little squares and circles. So this one would be a little circle. And then notice that these are all divided diagonally for the first four. All right, and we've shaded the bottom of the first two, and then we've shaded the top of these two. But then the third one is entirely filled in. Right? So maybe a reasonable conjecture would be that the next little circle is also entirely filled in. All right, and then that does fit with all of the patterns that we've seen, so that would be a reasonable conjecture. All right, how about 2, 9, 16, 23, 30? What would come next? All right, a good guess would be 37, if you see that pattern of adding sevens. All right. However, what if these numbers represent the dates of Mondays from a calendar in this particular year? All right, so maybe it's 2, 9, 16, 23, 30 as the dates in June, and then the next one would be the first Monday in July, right, which happens to be the 7th. All right, so another example, we just can't know for sure what that pattern is, even though we can observe some specific examples that lead to an idea or a guess, a conjecture of what comes next. Make a conjecture about the number of sections a circle is divided into when a given number of points on the circle are connected by chords. Okay, so review of chords from geometry. A chord is just a line segment that cuts across a circle. So in this first circle diagram, we have a circle with 1 point on the edge. Okay, and then next we have a circle with 2 points. Here's a circle with 3 points, 4, and then 5 points around the outside circumference. Right, and then what we're doing is just connecting all of those points with chords. Okay, so connect every point to every other point, and then count how many regions the circle is divided into. So this first circle, we have a point, but we don't have another point to even draw a chord. All right, so this one just has one region. The whole circle is a region. When we have 2 points, we have one chord, and we've cut the circle into 2 regions. Okay, this one with the triangle arrangement of chords. All right, that's 4 regions. And adding another point and more chords divides the circle into 8 regions. And then this is probably fairly small for you to even see. Okay, but this one is divided into 16 regions. Okay, so then if we wanted to take a guess, if we add a 6th point to that circle and take a guess as to how many regions there will be, right? Well, you might be suspicious at this point. We've seen some examples of where this type of reasoning doesn't work, but a reasonable guess might be 32. Okay, that's a really nice pattern. This is very geometric. We've got circles. These are nice, kind of well-behaved shapes that follow patterns. Right? Seems reasonable. However, that is not the case. And it actually turns out that no matter how you draw these points and these chords, you only end up with 31 different regions. And this is kind of cool because even though that really nice pattern didn't quite work out for us, there actually is a pattern to this. So here's a formula to calculate the number of regions in the circle based on how many points there are. All right, so n would be the number of points. And we could try this out. You go through and we know that, for example, a circle with 2 points was divided into 2 regions. All right, so go through this formula, plug in 2 for n, and work that all out and see if you come up with 2. minus 18 times 2 plus 24, and then divide the whole thing by 2. All right, so how in the world would anyone even come up with this? I like this example. I think it just really clearly points to the order and the design that we can see in the universe. It points to a creator, somebody who has ordered and puts these patterns into place. And it's just neat that we were able to discover a pattern that's as obscure as that. So what is the point of inductive reasoning? We've seen many times where it fails, it doesn't lead to a true conclusion. All right, so what's its purpose? Well, inductive reasoning can definitely be a useful tool in decision making, and we do use it very often in our lives. But it has one very obvious drawback, because you can very seldom verify conclusions for every possible case. You can't be positive that the conclusions you're drawing are correct. All right, so we use this with the weather all the time. If it's been rainy all week and the forecast says that it's going to rain, then you probably carry an umbrella with you because it makes sense that you're expecting that outcome of rain. But there's nothing saying that it has to rain. It may not rain, but it is better to be prepared and to use that inductive reasoning to kind of take a guess about what's going to come next or likely consequences, things like that. So throughout this course, you will reason mathematically to discover patterns and ideas and solve problems. So here's a little chart that I've created for you of how the process works. We start by observing God's creations and one's surroundings. Then we discover patterns in specific examples, and that's inductive reasoning. All right, so we're constantly gathering data and making observations, looking for clues, right, looking for patterns. And once we find a pattern, we often predict that this pattern will hold in general for other examples. That's called your conjecture. Then we test this general conclusion, the conjecture, to see if it does apply to other situations. If it does, all right, if we see that, yeah, it worked in our first 10 examples and I tried it in 30 more and it still seems to be a good pattern, then we want to try to use deductive reasoning to actually prove that this is true all the time. Right, so we use equations, facts, laws, or principles to prove that the conclusion will always be true. Right? If, however, you test that pattern in 30 other examples and you find, okay, no, it didn't quite work out, I don't think this pattern is actually the case. Right, so maybe our circle problem was a good example of that. If we had just gone and actually checked the next circle to see that there were only 31 regions, then we would know right away that pattern didn't work. So if that's the case, then what we've done, we've probably found an example that shows that the conclusion isn't always true. This is called a counterexample. Right, and we'll talk more about that in the next video. So then we try again. You look for a different pattern, or sometimes we move on to a new problem. So mathematicians will work on various problems, but sometimes they reach a point where they have to decide if it's worth spending their career on, because one of these problems could take years or even decades to solve. And if it's not that significant of a problem, if they don't think that that there's much use for it or that it will really advance the fields of math or science, then they might just move on and try something else. So then we go back to the beginning and we start with observations again, looking for patterns and clues and things that could lead to further discoveries. All right, we will stop there. Thank you for watching, and in the next video we will talk more specifically about counterexamples, conjectures, and using these two types of reasoning together, what their role is and what each contributes.